All right, 31 looks like I have a graph here, and it says find an equation for the tan line at P and the horizontal tangent at Q. And so I have this, am I on the right page? 4 plus cotangent x minus 2 cosecant x. And P is the point pi over 2, 2. So tangent to P. So I have a point, I need the derivative, right? So I can find the slope. There's my point. I need a point and a slope. So for my slope, I'm going to use the slope of the tan line would be the derivative at pi over 2, right? Y'all all okay there? So let's find the derivative, which should have been the hardest part of this. Definitely use this as you go through right now because we're just learning these. So we have derivative of 4 is what? And derivative of cotangent? Negative cosecant squared, and I'm doing it at pi over 2, minus 2, what's the derivative of cosecant? Negative cosecant, and I'm just going to fill in the pi over 2 here, cotangent. I'm assuming this is non-calculator. Oh, they let you have a calculator for this one? Mighty nice of them. But we can do it without one. Cosecant is 1 over sine, yes? So what is the sine at pi over 2? 1. So I've got negative 1 squared, okay? And it's going to be, this negative is going to be, the squared's going to come first because it's an exponent followed by the negative. So it's going to be more like this as you work through this one. Minus 2, again, this is negative 1 times, what's the tangent at pi over 2? 0. So if I flip that, oh, it's undefined, isn't it? Is cotangent undefined there? Are y'all sure? Yeah. Tangent's undefined. That means cotangent is 0. Right, because that point would be 0, 1. So cotangent would be cosine 0 over 1. So yes, it's 0. Right. Are y'all following what we did there? Tangent's undefined at pi over 2, but cotangent's not. They flip-flop. So this just ends up being negative 1. So what y'all got? My slope is negative 1. My point is pi over 2, 2. So my equation of my tan line, y minus 2 equals slope times x pi over 2. And I can just move that 2 over. Y'all okay? Sure. Part B, the horizontal tangent to the curve at Q. So I've already found the equation. Must be why you get to use a calculator. I've already found the derivative, right? Negative cosecant squared x minus 2. So it'll be plus 2 cosecant x cotangent. Everybody okay there? This is the derivative, but I used x's instead. I just took the derivative of the original. The derivative of cotangent is cosecant squared. Then there was a minus 2, but the derivative of cosecant is negative cosecant cotangent, so it became plus. Yes. Thank you. Y'all follow me there? Okay. So the question asked for the horizontal tangent to the curve. Now I can look at this and say that I think that's happening at 1. Ooh, I don't know that I can be exact about that though. Is that what'd y'all do? Nothing? Did y'all do this one? You set it equal to 0 and solve. That's what I was gonna do. But great day. Okay, well let's see what happens. I don't think that we can assume that that point is at x equals 1 unless they tell us and it's defined at x equals 1. Do you see what I'm saying? Do y'all see the picture there? They got that little, and then it looks like Q. They've got this horizontal tangent drawn at Q, which is more like right here. It looks like it's at 1, but I don't think we can make that assumption if they don't explicitly define it being 1. So I think we don't have any choice but to set it equal. This is part B. I'm going to add cosecant squared x here. And I'm probably going to get rid of 1 cosecant x. I'm going to say we probably need a well, what we can do, you'll see I don't always know how to do these right off. I think about them. Oh, that's subtraction. Well, I divided, so I did this. Cotangent is cosine over sine. Cosecant is 1 over sine. Which have common denominators. I'm getting somewhere now. Can I find where that equals 0? I can set the numerator equal to 0, and that should be something I'm able to solve. The bottom being 0 is not going to do anything but make me undefined, but if I set the top to 0, that'll tell me where it equals 0. So I set the top to 0, solve it, I get 1 equals, I'm trying to be a hero and do this without a calculator. Just because this, to me, if you've got exact unit circle values, it would definitely be a non-calculator problem. Divide by 2, so where is cosine? And look at what I'm looking at on this graph. I'm between 0 and looks like maybe pi. Where is cosine a half? So look at your unit circle. Where's cosine 1/2? I don't have a unit circle on me. Pi over 3. Oh, it's close to 1, but not quite 1. So it's a good thing we didn't assume. This is just the x value, right? We set the derivative equal to 0, so that's where it's occurring. So now I need the slope at pi over 3, and I need the point at pi over 3, because I need a slope and a point. We did all that just to find where it's occurring. We needed to know what that q value was, and that's why we did it. Do y'all understand what we did? I feel like no, y'all don't understand what we did. No? Okay. How do you find a horizontal tangent? Horizontal, that's right. That's where the derivative equals 0. So that's why we did this. But the struggle was finding where that equals 0. I could have put this on my calculator, found the x-intercepts, but it wouldn't have been exact values. I wouldn't have gotten pi over 3 because your calculator's not going to give you pi over 3, right? So I went through and did it by hand, and this ended up just being nasty trig manipulation until I got to the point where I could solve it. So as I go through, I'm constantly just trying to rework these trig functions until I get to something that I can solve. If you get to a fraction equaling 0, you can always set the top equal to 0 to solve, because that's when it's going to equal 0. And that's all I did there. And I found out that the horizontal tangent is actually happening at pi over 3. So it's not happening at 1, it's happening at pi over 3. So now to write the equation of the tan line, I need a point and a slope. So there's my point, and there's my slope, but I'm going to have to plug back in to find them. This was a kind of terrible part B on this problem for how easy part A was. All right, so let's do it. The slope at pi over 3, I'm going to use that derivative equation again. So negative, this is where you'll need your unit circle if you don't know your values. Pi over 3 plus 2 cosecant pi over 3 cotangent pi over 3. This is just 1 over sine, right? 1 over sine squared pi over 3. So what's the sine of pi over 3? What's the y value at pi over 3? Square root of 3 over 2. But I have to square that, right? So this is negative 3 over 4. You agree with that? All right, so, oh, but I got to flip it. The sine of pi over 3 is square root of 3 over 2. On your unit circle, if you go to pi over 3 and look at the sine value. At pi over 3, you should be at 1/2 square root of 3 over 2. So then if I square that, I should get 3 over 4. You square the top and square the bottom. And because it's cosecant, I have to flip it. So it's actually going to be 4 over 3. Now for this one, the cosecant of pi over 3 is 1 over what? Cosecant's 1 over sine. We've already determined what the sine of pi over 3 is. The sine of pi over 3 is square root of 3 over 2, but I need to flip it, so it's going to be 2 over square root of 3. And I need to do the cotangent. Cotangent is cosine over sine. Cosine is, here's my point at pi over 3. So cosine is 1/2. Sine is square root of 3 over 2. Yes, I think you're just saying yes to get me to hurry up and finish this problem because it's horrendous. Like, just be done with it already. Okay. This is just heavily steeped in the unit circle. All right, so negative 4/3 plus 2 times 2 is 4. Square root of 3 times square root of 3, is it 0? Oh my gosh, I'm an idiot, y'all. Y'all see what I just did? I already know the slope. Why do I already know the slope? I'm a dummy. It's a horizontal tangent. That was the whole point in the first part of it. I didn't have to do any of that. Nobody stopped me. Oh my gosh. That was why I did all of this. I said it equal. Oh my goodness. I didn't need to do all that. Well, at least I know we did it right because I got 0 whenever I did it. This is the only thing I need to do. I have the slope. The slope is 0. I need the point. I'm sorry, y'all. Okay, plug it in the original equation. Yeah, okay, sorry. My bad. I wish I could erase all that from that recording now. That's embarrassing. Okay, take the very first equation. Y'all are just chugging right along with me, too. I didn't say a word. Y'all know I'm often wrong. Correct me. Oh my gosh, I can't believe I did all that. All right. Such is my life. Better do too much than too little, I suppose. Cotangent of pi over 3. Have we done that yet? Yeah, look, we just did that. Oh, looky there. We don't have to do it again. 1 over square root of 3 minus 2. What's the cosecant of pi over 3? We did that too. 2 over square root of 3. Which is 4 plus, this is 1 over root 3 minus 4 over root 3, which is 4 minus 3 over the square root of 3, which is, I'm just going to rewrite that, right? That's my point. So my point is pi over 3, 4 minus square root of 3. My slope is 0 that we found twice, but that's okay. So it's y minus 4 minus root 3. Slope times x minus pi over 3. None of this matters because it's a horizontal line. A horizontal line is just y equals left. So I'm going to add that to both sides. So y equals 4 minus square root of 3. Great day. I made that immensely harder than what it should have been. No wonder y'all were looking at me like deer in headlights. It's fun. All right, what else on your homework? Be careful before you ask me because you might get more than you bargained for. 36. Find the second derivative if y equals theta times tangent theta. Theta is just a variable just like x. Treat it just as such. So the first derivative, I'm going to have to use product rule here because I'm multiplying two things together. So derivative of theta is 1 times tangent theta plus the first, what's the derivative of tangent? Secant squared, right? Derivative of tangent, or derivative of theta, sorry. Theta is just like x. If this was x times tangent x, it would be the same thing. So you do derivative of the first times the second plus the first times derivative of the second. Yes. I do not like that they're asking you to find this when you don't know the chain rule yet. You don't have to put the 1, but it's just so it's derivative of the first here times the second. This is where if you have u times v, the derivative of that would be derivative of the first times the second plus the first times derivative of the second. It's just the product rule. Oh, this is no bueno, y'all. Well, because to find the derivative of this, you're going to have to use the chain rule. Y'all don't know the chain rule yet. So I'm not sure. Yeah, like, chain rule's in 3-1 is the next section. Because you don't know the derivative of secant squared x. They didn't even put the answer to that one in here. Oh, yeah, they did. Oh, that is dumb. They found common denominator, so they said this is the same thing as 1 over, I'm assuming this is what they did, 1 over cosine theta plus theta over cosine squared theta. Because that would be, secant squared is 1 over cosine squared, right? Times the theta. And then they combined those to say, well, that's, get a common denominator, give this one a cosine, give this one a cosine, so that they have common denominator. Oh, I meant to say sine over cosine, sorry. Right now I'm just trying to figure out, this would be such an easy problem with chain rule. What? What? Where do you see 3 cosines? Here? Okay, so since this denominator was cosine squared, I gave this one a cosine to make them have the same denominator. But since I gave it to this one, because this one was squared, so they would have had the same denominator, but there was 2 in that one. There's 2 cosines in that. So secant squared theta is the same thing as 1 over cosine squared theta. But tangent theta is sine theta over cosine theta. So the tangent only had 1 cosine in the bottom, but the secant squared had 2. Yes. Yes. I'm sorry. Yes. I am going to say skip this because here's what they did. Then they did quotient property with an embedded product property, which is so dumb because when we get to chain rule, this will be a easy peasy problem, no worries. So I'm going to say skip this one, but be able to do the velocity, speed, acceleration, and jerk of these functions, but not for this particular one because this is silly to do all this. The other thing you could have done here, you still need, you've got a double product here. You've got theta times secant theta times secant theta. I was going to say you could do product rule, but you got two products there, so that wouldn't work either without chain. Okay, so as long as you can get that first derivative, that is velocity. You won't have, you could do speed. Speed would just be absolute value of that. You won't have. Oh, okay. Then yeah, stop at first derivative there. Sorry. I'm going to make a note of that one in this book, because how no, just the first derivative. No, without. Okay. Right there, that was terrible. What else? 38 and 39. The A and the B and the C only went with 33 and 34. I did the same thing just now. Right. Oh my goodness, I'm just not on it today. I'm sorry, y'all. All right, look at 38. Once I show you how to do 38, you'll know how to do 39. It says the 999th derivative with respect to x of cosine x. So y'all remember when we did imaginary numbers in algebra 2 and we did iterations? And I said I is the square root of -1, I squared is -1, I to the third is negative I to the fourth is, and then after the fourth one they started repeating. Remember? And then we said, well, we could find I to any power by just dividing by 4 and looking at the remainder, and it would give us the iteration that we were at. This is the same kind of thing. If I take the first derivative of cosine, what do I get? Sine. Negative sine, right? If I take the second derivative, what do I get? Negative cosine. If I take the third derivative, what do I get? Sine, positive sine. If I take the fourth derivative, what do I get? And then I'm back where I started and it loops back around. So there are 4 iterations for sine. Same thing happens with cosine. So if I divide 999 divided by 4, how many times does that go in? That means 249 loops around, right? Which doesn't even matter. I'm looping around the same 4 numbers. But then it goes through, 0.75 is 3 out of 4. So it would equal sine x. That's how many times it loops around. Yes. Yes. It won't be because you're dividing by 4. It'll either be 0, 0.25, 0.5. So this will be, oh, we got to go. No, that's right. That's right. Yeah. 0.25, 0.5, 0.75. Yeah. That makes sense? Same thing with the sin x. You would just go through the sin x in the 4 iterations and divide. So it was the 725th. You try this one. See if you get it. If it took 5 times to repeat itself, then you would have 5 iterations. You would divide by 5. If it took 10 times to repeat itself, you would divide by 10 and look at the remainder. Does that make sense? Yes, because, yes, yes. Because if you divide it one time, you get 1 divided by 4, which is 0.25, and that would be the first iteration. Look at it. Which one is it? What else from your homework? Which one? 49. This is a continuation of exercise 40. Did we do 40? Oh, okay. Oh, we didn't do linearization. Linearization is just writing a tan line close. Let's see, for values of x close to 0. We didn't talk about this a whole lot. They gave you an equation in number 40, though, that line is y equals x. And it says to approximate sine of 0.12 using that line, all they want you to do is put 0.12 in for x to tell you that y equals 0.12. That's all. And then you use your calculator to actually do sine of 0.12 and see how close it is to 0.12. Mm-hmm. Anything else? You want me to break? Yes. Yeah. Okay. Then we'll take a break. Use the identity sign 2x equals 2. Oh, they gave you the identity in this one. That was nice. 2 sine x cosine x. To find the derivative of sine 2x. Then use the identity. So we want to find derivative of sine 2x. And then we want to use the identity cosine 2x cosine squared x minus sine squared. That one's going to be nasty because we don't know the term. We'll discipline. To express the derivative in terms of cosine 2x. Okay. So derivative of sine 2x here, so we're going to replace this with this. Again, this is all because you don't know the chain rule yet. So what we're going to do really is find the derivative of 2 sine x cosine x. 2 is a constant. They are that coefficient, so I'm going to bring that out front, and I'm going to do 2 times the derivative of sine x cosine x, and this looks like a product rule to me. So here we go. 2 times derivative of the first. What's the derivative of sine x? Cosine x times the second plus the first. What's the derivative of cosine x? Negative. So this is going to be 2 cosine squared x minus sine squared x. And then it said to you, what? Write it in terms of, oh, well, look at there. They gave me this. They said cosine squared minus sine squared is nothing more than cosine 2x. So I'm going to say that this equals 2 cosine 2x. Nice of them to give me those equations. That's it. And then 42, same kind of deal. Is that said? No, 43. Oh, sorry, 43. Use the identity cosine 2x equals cosine x minus sine x sine x. They wrote that way because you're going to have to use double product rule like that. To find the derivative of cosine 2x. So derivative of cosine 2x is going to be the same thing as the derivative of cosine x minus sine x sine x. Okay. Well, the reason you're not doing that is because you don't know the chain rule. And you'll see why whenever we get to chain rule, you can't just do that. All right, so we're going to do derivative of the first, which is, what's the derivative of cosine? Negative sine times the second plus the first times derivative of the second. And then I have minus derivative of the first times the second. Well, it's subtracting all that, so that's why I put the subtraction with the big brackets here. Plus the first times derivative of the second. These are the same, but there's two of them. So negative 2 sine x cosine x minus, and then there's two of these, 2 sine x cosine x. So express the derivative in terms of sine 2x. What's sine 2x on your double angle thing? That's sine 2x. So it'll be negative 2 sine 2x, because there's two of them. So is that what you said? That is right. Look at your rainbow sheet, your different colored sheet. Sine 2x is 2 sine x cosine x. So it said to express it as so that would be negative sine 2x minus negative sine 2x. Oh, minus positive. So, which would be negative 2 sine 2x. What? No, because it asked me to, it said express the derivative in terms of sine of 2x, which is that double angle identity. Okay. I heard. All right, let's take a look at this. I'm going to just go over it quickly with you. Make sure we're all on the same page here. The graph shows the position of a particle moving along a horizontal coordinate axis. So this is the position graph. That's what we have to remember. Be very careful about what's being given to you so you know what it is you're trying to find. So the first says, when is the particle moving to the left? So as I look at this sheet, I've got this little, does something like this. And you've got the exact values on your sheet. But when is it moving to the left? What am I looking for here? Negative what? Slope. Why am I looking for negative slope? What's the slope telling me? So what? The direction and the velocity, right? The slope is the velocity because that's the first derivative. So where is my slope negative? Right there, from 5 to 7. Right. When is the particle moving to the right? How do you know? Positive slope. That's exactly right. When does it stop or standing still? That's exactly right. Graph the particle's velocity and speed were defined. So I'm going to actually have to find the slope here, right? What's the slope of this first little piece? Looks like it goes up 2 over 1. The slope would be 2. So velocity up to 2. How about here? What's the slope? 0. Yes, that's exactly right. How about the slope of that next piece? Looks like it goes up to 4 and over 1. So up to 4. Then that last one's the only place it's negative, and it looks like it goes down to 4, but over 2. So it looks like the slope might be negative 2. So there's your graph of velocity. How is the graph of speed going to be different? It's the absolute value. So the only thing that's changing is that one piece is going to become positive too. That's exactly right. When is the particle moving the fastest? That's exactly right. When the speed is the greatest. So it's moving the fastest. Where is it 4 there? From 3 to 4. Y'all good on those? Because the speed's the greatest. All right. Let's do a harmonic motion problem. I think about these like springs, like put like a weight on the end of a spring and it starts bouncing up and down. That would be like a harmonic motion problem. Let's look at number 12 together. You'll have 11 through 20 for homework tonight. We'll do 12 together. So it says a weight hanging from a spring bobs up and down with the position function S equals F of t. S is in meters and t is in seconds. What are its velocity and acceleration at time t, and describe the motion? So when it says describe the motion, I'm looking for words here. So I'll find everything, but then I'll have to go in and do my sentences where I describe exactly what's going on. I know. All right, well, let's do it. What are its velocity and acceleration at time t? So here it says that S is 7 cosine t. So velocity is what? First derivative. So 7 times, what's the derivative of cosine? Negative sine. So the velocity is negative 7 sine t. No, because it's a coefficient, it's a constant coefficient, it's not a variable there. How about the acceleration? Second derivative. So negative 7, what's the derivative of sine? Cosine. It doesn't ask you, but what if you had to find the jerk? There you go. How about the speed? Absolute value of negative 7. Well, that was easy. What's not so easy is whenever it says describe the motion. So when I describe the motion, I want to tell where my particle starts. I want to tell what direction it's moving, when it changes direction, what happens, all that good stuff. So first thing I want to know is, where does it start? How do I find where it starts? Put what in the calculator? What are you going to do? Y'all know this. What function do I use to find the starting point? The position function. That's exactly right. I want to know where it was when it started. If I want to know where, I'm going to use position. So I want to find S of 0. When time is 0, where does it start? Okay. So S of 0 here would be 7 cosine 0. Well, what's the cosine of 0? Cosine is x. So at 0, what is the x value? 1, right? This point is 1, 0. So cosine at 0 is 1. So this tells me my particle starts at 7 meters. So it doesn't start right at 0 on my ruler. He's starting at 7. Are y'all okay there? Okay. Next, let's look, because I need to know which way he's moving, right? And I need to know when he changes direction. So what am I going to need to find? Anybody? Velocity. What about velocity do I need to find? When does something change direction? When velocity equals 0, whenever it changes sign. That's right. Let's do a sign chart. When is, all right, so velocity is negative 7 sine t, right? When is that ever 0? Well, I can divide both sides by negative 7, right? That's not going to impact anything. So when is sine 0? So again, back to your unit circle, sine is y. So where are the values where sine is 0? At 0, where else? Pi. Are those the only places? So every pi is where sine is 0? Agree? Disagree? Everybody okay? No place else, right? So you see why we got those values. Okay. Remember we talked about simple harmonic motion, just like that weight bouncing, boing, 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 boing. So does it make sense that it would be changing positions that many times? From up to down to up to down to up to down, right? All right, so we got 0. We got pi. We got 2 pi. We got 3 pi. And hopefully we'll pick up a pattern and this will keep going. This is going to be velocity. This is going to be position. I just divided both sides by -7. I'm solving it for t is what I'm doing. From 0 to pi. Again, back on your unit circle. I don't have one up here. Between 0 and pi, right? So I am in the top half of the circle. I'm looking for sign, right? Because that's velocity. Is the sign positive or negative? Remember, velocity is -7 sine t. So I'm going to be multiplying by a negative value. Is the sign positive or negative between 0 and pi? Sign is y, so it's positive, right? Which means velocity is going to be negative. Okay. Sine, but you got to times it by -7 because velocity is -7 times the sine of t. All right, so between 0 and pi, right? The very first thing I said was the sine of t. What's the sine, S-I-G-N, of sine t? Between 0 and pi. So the top half of this whole circle, the sine, which is the y value, right? Because it's above the x-axis, is always positive. A negative times a positive is always going to give me a negative. So first, when this weight drops down off the spring, it's going down, and that makes sense, right? Are y'all okay? Are y'all with me? And then between pi and 2 pi, so now on the bottom half of the circle, it's positive because I'll have a negative times -7, which would be a negative times a negative, which is a positive. So then it bounces back up. And in fact, knowing what I know about the unit circle, every pi, the sign changes on y, right? So this should go negative, positive, keep going negative, positive, negative, positive. So it should do this. Say again. You're exactly right. You're exactly right. So let's think about this. I started what position did I start? 7. From, is it feet? From time 0 to pi, what am I in seconds or minutes or what? Okay, seconds. I move down, and I can even say 2. Well, where do I move to? So I'm going to do S of pi. That's going to give me position, right? Where am I then? S was, lost my position function, 7 cosine t. What's the cosine at pi? -1. So I start at 7 feet. From time 0 to pi seconds, I move down to -7 feet or meters or whatever it is I'm in, right? Then change direction and move up from pi to 2 pi seconds. Ending at, then what's my position at 2 pi? 7. What? I plug this into position where you see 1. And it's 7. Oh yeah, because position is 7 cosine t, and we put 2 pi in for t. So cosine of 2 pi. So if I go to 2 pi, I'm back at 0, and that's 1. So I went pi, 2 pi, back to 0. Does that make sense? And then I would continue that motion. So it's constantly bouncing between 7 feet and negative 7 feet. When is it moving the fastest? Yeah, I'm just testing your knowledge right now on what's going on with this spring. This is 7. This is negative 7. I'm just going to sketch the position function for just a minute. Pi, 2 pi. I'm going to graph position. It starts at 7, right? That was really quick for, thank you, Drew. It starts at 7 and it moves down until I get to 2 pi. Until I get to pi, right? And then it moves up until I get to 2 pi. And I know that this is a cosine graph, right? So it's going to do this, right? So this is actually going to be pi over 2, 3 pi over 2. So where is it moving the fastest? Why? Look at you. Very good. About here? When's it moving the fastest? At pi over 2, because that's when the slope is the steepest. So here I'm a horizontal tangent, right? And I'm approaching a steeper slope. When I get here, that's as steep as it ever gets. And then it starts evening back out to come around to this 0. So it's the steepest at every half pi. So where is it moving the fastest? Well, it's moving the fastest at every half pi. So it drops and it goes faster and then slows down and then bounces back up and then. Does that make sense? Does everybody see what's going on with the little weight on the end? I feel like no. Y'all okay? Henry, you look so sleepy. At every half pi, yes. All right, y'all want to do another one, or you want me to just set you loose? I think I'll set you loose because. All right, you're going to do 11 through 20. We talked a lot more than what you will be required to do on these problems. I just wanted to make sure you understood exactly what was going on. This is position. Yeah. No, that's position. So I was looking at the slopes on position.